Welcome, CalcBC. This is lesson 2.5, absolute extrema and the mean value theorem. Let's begin. So, a few definitions right here. We have the idea of the absolute maximum and the absolute minimum. So these are what we sometimes call the global maximum minimum. Max and mins are going to be y values, and it's the biggest or smallest y value on the function. Now we have this concept of relative maximum and minimums. And the idea is like, this is the maximum or the minimum in this small area of the function. So you might have a function that looks like this, with the curve down here and up to here. Well, our maximum's way up here, and the absolute minimum's way down here, but you can see like right here and right here, these are relative maxes and mins. So they're kind of like the bottoms of like the mountains and valleys of a graph. And if you have a bunch of those, each of those would be relative. Now, extrema, another word, are extreme values. So these, sometimes it's just another word for the absolute maximum and minimum. So just another word for that. And critical numbers, so these are the actual x values where the maximum and minimums happen. So just a reminder, the maxes and mins are y values, where the maximum happens are x values. These are usually critical numbers or endpoints. And critical numbers are the x's. So yes, absolutes, you always have to check the endpoints as well as the critical numbers. So how do you find the absolute min and max? So we call it the candidate test. So you got to find all the critical numbers of the function. And you got to find the y values of each critical number. Usually you do that through some kind of table. And you also want to check each endpoint of that on the interval. Usually it's a closed interval. And then you want to choose the least and greatest number. Biggest and smallest are your absolute min and max. So just a reminder, your absolute min and max can happen at the critical numbers or endpoints. That's why you have to check each of those. And relative extrema only at the critical numbers. You're not going to have those at endpoints when we're talking relative. So let's do some examples of this. So I have a picture of a graph right here. I'm going to ask these questions. This is a function. What is the absolute maximum of f? Well, the absolute maximum is going to be the highest y value. If you're looking at this picture, it's going to be here. And so the highest y value is going to be 4 because it's at the height is 4. At which x value does f have the absolute maximum? Well, that's an x equals negative 4 because negative 4 is right here. So the maximum is 4. Where it's at is negative 4. What's the absolute maximum point of f? Well, as an ordered pair, I can write that as negative 4, comma 4. What's the absolute minimum of f? So we have to look around here. And so this is kind of weird. The absolute minimum, it looks like it's right here. But this is a weird case where we don't actually have a point right here. We do not have an absolute minimum of f. I know you can say like, oh, well, would these be minimums or this one? But since we know like it's approaching negative 2, but doesn't actually reach this is a funky case where we don't have a minimum. It doesn't happen too much. At what x value does f have a relative minimum? Okay, relative minimum. So like minimums at around a certain point. So minimum is going to happen like right there and right there. And so it's like of an interval. Those would be good ones. That's not going to work right there. So these two, what x values, we're going to say at x equals negative 3 and at positive 1. Now, where x values does have a relative maximum. So relative maximums, like they're critical numbers, they're not endpoints. It's just going to be right here. So we're going to say x equals negative 1. All right. So I want to use a function. A lot of times we do it this way. I might say, find the global extrema. And you're like, what are those? Well, it's the absolute min and max. So there's a bunch of different ways to ask the same question. But this just says find the absolute min and max. So the first thing you have to do is you have to check and find all your critical numbers. So I'm going to derive that function. So your f prime of x is going to be 3's are going to cancel. It's going to be 1/3, I'll do the work, times 3x squared minus 2 times 2x, which is going to be cancel on the 3's, x squared minus 4x. And you're going to set that equal to 0. So solving that, I'm going to factor on x. So it's going to be 0 equals x times the quantity x minus 4. And so my two critical numbers are x equals 0 and positive 4. So I want to check, and then when I have to check, see which is actually an absolute max or min, I'm going to create a table. I like just doing an xy table just like this. So it's going to have my 2 points in between 0 and 4. Oh, and then we have this interval from negative 1 to 3. Uh-oh, there's a problem here. So that 4 was a critical number, but it's outside the interval from negative 1 to 3. So that's actually not on my list. Only the 0 is. So I have to check the endpoints, negative 1 and 3, and I'm going to check 0. So when you plug in -1, now you're plugging this in to the f of x function, not the derivative. I want to know the y value, and the y value is not the derivative. So when you're plugging that into f of x of -1, I get 1/3 times -1 cubed minus 2 times -1 squared. -1 cubed is -1, so it'll be -1/3, and then that'll be minus 2. So -1/3 minus 2 is the same thing as 6/3 when you're subtracting it, so it'll be -7/3. Now if you plug in 0, you'll get 0. You plug in 3, oh boy. 1/3 times 3 cubed minus 2 times 3 squared equals, this is 27 divided by 3, so 9 minus 9 times 2 is 18, so this will be -9. So our absolute max, I'm going to say happens, the biggest y value is 0, so it happens at 0, 0. And then the absolute minimum happens at the point, well, -9 is smaller than this, so at 3, -9. So those are my answers. If it says global extrema, it might ask for the points here, so that's how I put it, or it might ask for like the actual y value, so it'd be 0 to -9, or my global extrema, or absolute min and max. I can do another example, but we'll save that for class. Mean value theorem. So here's some examples to kind of explain what's going on with mean value theorem. I might want to draw a secant line between each of these endpoints. I'm going to draw a line just like this. Actually, I want to do it a different color. I want to do it in purple. So I'm going to draw a line between the endpoints. Okay, this secant line means that it crosses a function twice, or more than once. And then draw all the tangent lines parallel to that secant line. So each of these, I'm going to duplicate these. I think I can do it that way. And it's, where would be a parallel line, a tangent line is parallel? About right there. You see how it looks like a tangent line? Let's take this example. I can duplicate this, and notice it'd be a parallel tangent line might happen there, or it might also happen right here. So there's two spots. Oops. And now this last one. So this one's kind of neat. I'm going to duplicate this and go, oh, oops. Where is that going to be parallel? Well, it's kind of nowhere. Like, that doesn't work. That's a sharp turn right there. That's no tangent line. This actually doesn't have any tangent lines that'll be parallel. So the idea here is that like sometimes you have your secant line, or like the line connecting the two endpoints, and the slope of that line should match some tangent line between those 2 points. But let's do another example here. So I want to draw a secant line between 2 points. So I'm going to draw it between 2 points right here and the 2 points right here. And what I want to do is I want to like approximate the value, or the x value, where that's going to be a tangent line. So doing this again, that might be a tangent line about right there. So the question becomes, sometimes we ask like, okay, I know it's tangent here, what value of x, or what value of c, which is an x value, it's approximately going to be when c is approximately equal to 3. Because that's about where it lines up. What about for this one? Well, what values for x are going to match that tangent line is going to be equal to that slope? Well, it's going to be like, notice that kind of lined up with 2 points. It kind of lined up like here and right here. And then if we did another tangent line, no, don't move that part. It's going to line up like right there as well. So like a third point. And this is outside of those 2 points. So this one's going to be approximately, let's say, 2.5. And up here, I don't know, 4.5. And this one's going to be roughly 3.5. So there's 3 values where that slope of that tangent line is the same as the slope of the line between the 2 endpoints. And this is the idea of the mean value theorem. So, and think like rate of change, we talked about that. So if you have a continuous function and it's differentiable, then there's some number in between where the slope of the endpoints equals the slope of the tangent line. So slope between so you have to find the slope between the 2 points, and then it's going to match some derivative at some point in between there. It's going to be the slope of some point. And that's the idea of the mean value theorem. Note the function has to be continuous and differentiable. If you go back to this example, it's not going to work for this function right here because we're not differentiable at that point. So that is not differential between a and b. These two are smooth curves, so they will be differentiable. And the same thing in these cases. All right, let's do that. Let's see what actually looks at a problem, though. If I've given a function like this, I'm going to find all c, so find all x's, which satisfy the mean value theorem. So first of all, let's differentiate this. The first question you might have is it going to be continuous on this interval? Now, divided by 6, it's not going to be continuous when x equals 0. That's discontinuous. You can't say x equals 0 because you're dividing by 0. But that's not on my interval, so we don't care. So we're continuous on this interval from 3 to 6. So the derivative of this function, derivative of 3, 0, and negative 6 over x is positive 6 over x squared. All right. Now, again, this is differentiable everywhere except x equals 0, so we're good on that domain. So I'm going to find when that satisfy the interval. So we have to check our endpoints here. I got to check the slope between the 2 points, and I should have done it with the original equation. So I like making a table for this, x and f of x, or y, and you're checking from 3 to 6. So if you plug in a 3 to this equation, you get 3 minus 6 over 3. So 3 minus 2 is 1. And if you plug in 6, you're going to get 3 minus 6 over 6, which is 2. So what's the slope between those 2 points? Well, it's going to be the change in y. Your slope m is the change in y over change in x, which is going to be up 1, and it's going to be up 3. So that's going to be 1/3. So I want to figure out where the derivative, what value of x does the derivative equal 1/3? So I'm going to take this derivative I found and say 1/3 equals 6 over x squared. Now let's do some algebra. And when your equal fractions equal each other, I multiply both sides by x squared. So I get x squared over 3 equals 6. Multiply by 3 on both sides. You get your x squared equals 18. Square root both sides. X equals plus or minus square root of 18. I'll leave it like that. You can reduce that if you wanted to. Just do that as a reminder. It's the way I always like doing it. 2 circle pair square alone. So that's equivalent to plus or minus 3 square roots of 2. Now, what's in that interval? Well, negative 3 square roots of 2 is not. So it's only on the case when x equals positive 3 square root of 2. So that's your answer. All right, that's going to be it.